Ladies and gentlemen, boys and girls, welcome to another lesson from Transparent Physics. In this episode, we will be continuing our series on energy, work, and power. And specifically, we were going to be introducing work. And very briefly as an aside, if you find the content of this video to be helpful, please consider liking the video at the end or during. You don't have to wait till the end. If you have any questions about what I say, please leave it in the comment field. And to find out what's coming next from Transparent Physics and to help the channel grow, please consider subscribing. And specifically in the context of this lesson, we're going to be defining what work is. We're going to be introducing a simple equation for work and then a better equation for work. So let's get into it. All right, then what is work? And if I added an extra subscriber for every time I said this next phrase, I'd have like 23 more subscribers on this channel. And the idea is that when we have words that also exist in the English language, those words come with their own baggage. They come with a background of meanings and applications. Work, perhaps more so than a lot of the words we use. Work means a lot of different things. To the best of my internet research, it harkens back to around the 12th century, and even then it had a wide variety of applications in terms of just simply doing something, to maybe more specifically sort of a physical labor or toil sort of scenario, or even a broader idea of something that you did, like a trade or a craft that you were able to do. A lot of ways you could sort of think about it in terms of expending labor in kind of a useful way, which isn't too bad for the physics per job. And the everyday definitions go in a lot of different directions. And perhaps it makes it a little easier then that in physics, there is one specific definition for work. In terms of the physics definition, you might be asking yourself, well, why do we even talk about work in the same context of energy? Well, it's because work is very closely related to the idea of energy. Work is a way to transfer energy to or from an object via a force applied to an object over a distance. And that energy transfer can manifest in different ways, but as far as introductory physics goes, we're going to be talking about adding or removing kinetic energy and then adding or removing potential energy. And even in that potential energy, we're probably just going to limit it to gravitational potential energy. But it has to be with the application of a force, and the object has to move over some sort of displacement. Now, when you are applying a force, we're going to get into this in a little more detail when we get to the equation. But the force has to actually be acting in the direction of the object's motion for that force to count. And when I say direction, I mean XY sort of direction. It doesn't have to be pointing the same way. For example, if we talk about the X direction as horizontal, you could have a force acting to the right. You could also have a force acting to the left. Those are both in the same X direction in terms of their ability to add or subtract energy to the object. And just a quick reminder, when we're in this section, this work, energy, power section, when we are looking at scenarios to solve, a lot of them are going to seem similar to things that we talked about earlier. The physics that we're talking about here isn't really expanding us into being able to talk about different scenarios. It's allowing us to look at scenarios we looked at before in a different way. I have to admit, I waffled a little bit as to whether or not to include this in the introductory work discussion, but I think it sets up our scaffolding nicely enough that it's worth the investment. And it's the idea of work on something versus work by something. And this nuance comes back to the idea that when we talk about work, work is a transfer of energy via a force. And back in transparent physics, when I introduced the idea of forces, a force is a push or a pull acting on one object from another object. So every time you have a force, there are always two objects involved. You have the object that is exerting the force, and you have the object that the force is being exerted on. So this isn't anything new, the idea that a force always involves two objects, but it does sometimes take kind of special emphasis in this section. Maybe more so as we get into it a little deeper. But specifically focusing on the objects and their roles in this energy transfer can help us understand things better. And we're interested in, what object is the work being done on? And often we're interested in what object is the work being done by. And a lot of times when we're trying to be very precise, we add some subscripts that go on and then by. So when you read a set of subscripts, for example, the work done on the car by friction, it might sort of show up in the subscripts as W sub C sub F. And then when you're looking at that, you know what object is having the energy transferred into or out of it, potentially, and what object is doing that transferring. I know that on-by thing can be kind of confusing. So let's look at this in the context of a sample scenario. You're pushing a couch across the, living room floor or something. And if we look at the forces acting on an object, we can use those as a window into the work being done on the object. And we've done this before. We've looked at the forces acting on an object on this channel. So hopefully this won't be too bad. So if you take a look at this, sort of imagine yourself what kind of forces would be acting on this couch as it's being pushed. Well, gravity is going to be pulling down on it. The floor, the surface, is going to be pushing up on it. Astute visitors to this channel might realize that that force also could be known as the normal force. Then we obviously need a push on the couch, and then let's assume that there's some friction resisting it as well. So we have 4 sets of forces. Again, astute observers might recognize that the push force was drawn longer than the friction force. So the visual implication of that is that you're pushing with more force than friction is resisting you with. So in the larger context, this couch would be accelerating. All right, so every force is a candidate for possibly doing work on the couch, although not every force ultimately will do work on the couch. So let's basically translate each of these forces into works. And there we go. Every force could potentially turn into a work. Now, not every force is going to make this transition because some of these might end up being 0. So we need to take this concept of every force is potentially work and turn it into practice with the benefit and application of an equation. Okay, I'm going to resist the temptation to sit back and say, whew, that was a lot of work so far. I am not going to make that pun. But it is a good time to stop and take a sip of tea. Or if you haven't made tea for yourself yet, maybe stop. You've earned it. Go brew yourself a cup, come back. We'll finish up. And at this point in your physics course, there's probably 2 different ways that your course could go in terms of what equation they're going to introduce. There's what I call the simple equation. The simple equation is just work equals force times displacement. It really often is just force times distance. How much force do you exert and how far does the object move? So if you take force times displacement, when we do simplify that into variables, work is abbreviated as a W. Be careful about that. This might be our first example where a letter gets used twice and work is absolutely not equal to the weight. If we take a look at the units, force is newtons, displacement is in meters, and when we take newtons times meters, we get Newton meters, which is joules. You might remember that because that is the unit for energy introduced earlier in this series. And this equation's okay. I mean, it's fine for a lot of basic introductory courses, but it does assume that force and displacement are pointing in the same direction. And that's not always going to be the case. So I'm not a huge fan of this equation, and I'm going to show you a better one. So there is a better equation for work, and it is a little more complicated to look at, but if you take the time to study it, it really pays off in spades. Work equals F d cosine theta. You can see there's those 2 little marks over the F and the D. I call those vector hats, and they remind us that the force and displacement quantities are vectors, and specifically vectors have a magnitude and a direction associated with them. And the important part of that for work is that direction, because the next term, cosine theta, relates to that. Interestingly, a side note, if you notice, work itself doesn't have a vector hat on it. Work is not a vector quantity. It doesn't have a direction associated with it. It's simply, do you do work or do you not do work? Now, that doesn't mean that it can't be positive or negative. Things can be positive or negative and still be a scalar quantity. It's just that positive and negative doesn't indicate a directional aspect to it. It simply indicates, sort of, are you adding or removing, I guess. And that theta term is the angle between the force and the displacement vectors. And a challenge I sometimes find in this point of the course is, usually up to this point, every time I've been talking about angles, they've always been sort of locked towards the positive x-axis. If you're a longtime viewer of this channel, when we do vector calculations in general, we always take the angle with respect to the positive x-axis. But in this case, we are not going to. That angle is the angle between the force and the displacement vectors. So if you draw a force vector on a piece of paper, and then you draw a displacement vector starting at the same point as the force vector did, whatever the angle is between those two vectors is theta. Let me show you some examples of this. So if the object is moving to the right and the force is also acting to the right, I offset them a little bit, but realistically they should be sitting on top of each other here. In this case, the angle between them would be 0 degrees. Sometimes I sort of tell kids to imagine that it's sort of like alligator jaws. And right now the alligator jaws are closed, so the angle is 0 degrees. So that's not a big deal. But it's also important to note that if the displacement was pointing upward and the force was pointing upward, what's the angle between those? A lot of kids would instinctively say 90 degrees because they're used to saying straight up is 90 degrees. But the angle between the two vectors is actually still 0 degrees. And this is a big adjustment for kids to make. It doesn't matter the exact orientation of the vectors, it only matters the angle between them. So we could have displacement return to the x-axis again, and then the force is pulling up at some angle with respect to the displacement. Now again, it's lined up with the x-axis here, but that's not the important part. We are just interested in the angle between them. So in this case, it would fall back to sort of a familiar idea, where if displacement's sitting on the horizontal axis, then the angle would work out kind of traditionally with respect to the positive x-axis. But that's just a coincidence because displacement's acting in that direction. If we instead put displacement up at some angle, we measure with respect to that displacement. We no longer measure with respect to the positive x-axis when we're calculating work. And generally, it's just the magnitude of the angle between the force and displacement vectors. It's very rare that I would ever use a negative angle for that. I'm simply interested in how big is the angle between the force and the displacement vector. In fact, now that I say it out loud, I don't think I ever in my career have ever used a negative angle in this equation. I always just use the magnitude of the angle between the force and displacement vector. So in this case, we'll just arbitrarily say that might be, say, 120 degrees. And if you put a protractor to the screen, it's probably not exactly 120 degrees, but you get the idea. So in all these cases, theta is the angle between the force and the displacement vector. It is not an angle with respect to the positive x-axis. All right, this is a natural stopping point. Just as a reminder, when you're using work outside of the context of your physics class, it has lots of definitions and lots of baggage associated with it. You're going to have to sort of uncouple that moving forward in physics class. When you discuss work, it's simply a way of understanding how energy gets into an object or is removed from an object. And where we left off by introducing that better equation, we're going to explore that in more detail in the next lesson, and that trigonometry, that cosine of theta, is going to prove extremely important in analyzing the work being done on an object. And as always, thank you for watching this episode. Hopefully I've made the concept of work from a physics perspective a little clearer on this lesson from Transparent Physics.